Today we're going to be talking about learning cube strategy in backgammon with neural networks. So in backgammon, there's a doubling cube that allows players to raise the stakes of the game, and when to give the cube, when to take the cube can be learned as a neural network function. So what is backgammon? It's basically a racing game, right? Players are racing to get their checkers off of the board by rolling 2 dice, right? And if they were only rolling 2 dice, that wouldn't be very interesting. Whoever rolled the bigger numbers would win, but the checkers can also block each other. And so at the same time that you want to consider moving your checkers really fast, you have to consider your opponent might be doing the same thing, and you have to trade that off with blocking your opponent's checkers. And the goal is to get all of your checkers off of the board before your opponent does. So what are some previous results in AI backgammon? Practically all of the strongest backgammon AIs today make use of artificial neural networks. The neural network basically is trying to compute an evaluation function given the situation on the board. Typically it does that by estimating the probability of winning and losing from the current position. That's also known as equity. Most backgammon experts call the probability of winning equity. And once you have a good function for that, you can improve upon that by having a search tree, right? So think 2 or 3 moves ahead. Think about what these positions down here are worth, and then work your way up, right? One player is trying to your opponent's trying to minimize your probability of winning. You're trying to maximize, and every time the dice is rolled, there's an average involved, right? That's called expectimax. And what are some gaps in previous work? Well, all of the neural networks to this day have only looked at the state of the board without regard to the situation of the doubling cube. In a game of backgammon, the doubling cube can be in one of 3 different positions. It could be held by one of the 2 players, or it could be in the middle of the board. And as far as we know, there haven't been many attempts at trying to consume that as part of your function. So what do they do instead? They approximate what we should do with the doubling cube based on what are known as doubling windows. Basically, if my win rate is between so and so, I'm going to double. If it's between so and so, I'm going to take. And a big gap of doing that is that it ignores the volatility of the current position, right? You're only looking at the win rate. You could have 2 positions that have very similar win rates, but one of them is bound to change very fast in the next couple of moves. And that can affect whether or not you double, right? If it's very volatile, you might want to think about if your opponent might double back at you, right? So how do we score a backgammon game? First of all, each game without the doubling cube can result in 1, 2, or 3 points. There are certain conditions called gammons and backgammons that score 2 and 3 points. Basically how far ahead you were when you won. And then the doubling cube doubles all those scores, right? If your doubling cube says 4 and you win a gammon, which is normally 2 points, that game is worth 8 points to the winner. And what do those points mean? Well, there are 2 different ways to score. There's the money game where there's a wager involved, usually a few dollars per point. I've seen games that are worth hundreds of dollars a point. And basically the winner collects that much per point from their opponent, right? And that can get pretty ridiculous fast because the doubling cube can go, well, it can go very high, right? But usually in a money game, I've seen it go up to 16 or 32 easily. In a match game, the game is played to a certain number of points, usually between 3 and 25, and there's no benefit for scoring more than the threshold, which is what makes this paper interesting because sometimes extra points are worth something for one player but not his opponent, right, because of the way scores are rounded down to the threshold. So what does the doubling cube do? Well, it doubles the stakes of the game, and when does it happen? Well, a player before rolling the dice decides he has a really good position and offers a double. And the opponent can immediately surrender and lose the current stakes of the game, right? If the cube was on 4, one player says, I'm going to double to 8. the opponent can say, "I'll drop," and the doubling player would immediately win 4 points and they would start a new round. Or the opponent can take and the game is now worth 8 points and they play on and it could be doubled again, right? Now the interesting part is that the opponent who accepts the double now holds on to the doubling cube and is the only player who can double next, which is what makes this a risky decision, because now going forward, if your opponent were to swing the game around, he could double, but if you swing the game more, you can't double. So holding the doubling cube almost has some value to it, right? And the point of this paper is to try to quantify that value with neural networks, right? Now, something interesting happens when one player is getting close to winning. So in this position, apologize for the typo, this is really a match to 5. Player 1 has 4 points, player 2 has 2 points, and we're playing up to a match at 5. Player 2 has nothing to lose by doubling, right? If he loses this round, he loses. And if he doubles, he could potentially win 2 points, right? So this is a no-brainer to double, which is what led to the introduction of the Crawford rule. So when one player first scores a point shy of winning, the next game is played without the doubling cube. It's called the Crawford round, and subsequent rounds called the post-Crawford can be doubled as usual. And in fact, usually the trailing player will double immediately. Now there are some special cases that have their own unique strategies. First of all, most experts generally like to describe the score as how many points away from winning, right? If you're 12-9 in a 15-point match, experts will usually call that 3 away, 6 away. And the reason for that is because you can have 3 away, 6 away with other match scores, match games as well, right? It makes it easier to compare games that really have the same result, right? Now imagine you have a game where both players are 1 away, or let's say one player is 3 away, another is 5 away, but the doubling cube is up to 8, right? And whoever wins that round wins the entire match. We call that a double match point. And so every double match point has the same flavor, right? That's why it's useful to have a name to this so that we can focus, we can learn something from one double match game and apply it to another, right? Now, sometimes a round could be a match point for one player but not the other, right? So for example, again, let's suppose one player is 3 away and the other is 5 away, and the doubling cube is at a 4, right? Now when that happens, another condition could happen. If the opponent who is not at the match point cannot double, right, whether it be because of the Crawford rule or they're not holding the cube, neither side's going to double, right? The player who is at the match point is clearly not going to double because it would only give his opponent a benefit, right? And the opponent can't double. We call that a cubeless-match point, right? It's a match point for one player. For the other who can't double, it's not, and the doubling cube is not going to come into play for the rest of the game, right? And all of these 3 games have their own kinds of flavoring and strategy, and it allows us to generalize from one position to another, right? Every double match point has similarities. Every cubeless match point has its own similarities. Okay, so before we get into the neural networks, it helps to solve some of the positions so that when we arrive at them, we instantly know the value and can stop our learning from there, right? When there are fewer than a certain number of pieces, the number of combinations on the board really dwindle. So when each side has at most 14 checkers, and all of the checkers are on the home board, right, on the 6 points of the home board, there are only about 1.5 billion such endgame positions. And so we can pre-compute who's going to win and who's the probability of each side winning, right? Now here's the tricky thing. If the doubling cube is still in play at this point, it gets tricky because the importance of points are not linear, right? If you're 2 points away from winning, the utility of winning those 2 points is not twice as much as the utility of winning the 1 point. And if you're 8 points away from winning, the utility curve of those points are very different, right? That's called the match equity table, and we'll get to that later. And so our endgame table, as far as we know, can only be used when there's no doubling involved, right? So for the two cases that we talked about, the double match point and the cubeless match point, can we make use of this table? It's kind of an open problem whether or not you can use an endgame table in the general case. I encourage my my viewers to look into that. Now, how does a neural network work for backgammon? Well, first we're going to break down our backgammon rounds to the three classes we talked about. The double match point, here no cube is used and the round may end in one of two different outcomes, right? You either win or you lose, right? Because that round determines the match. You have the cubeless match point. Again, no cube is used, and there's actually four different outcomes that can happen, right? The match point player might win, or the opponent might win, or win a gammon or a backgammon, right? So there's four different outcomes. Now, every other case when the cube is in play, the round could have quite a number of results, right? Either player could win, and they could win practically any number of points, right? Bounded by however many points your match is being played for. And what's the goal of the neural network? Remember, a neural network is basically a giant math function that's calculating something, right? What are we calculating here? Well, we're trying to predict the probability of each of these outcomes happening, right? Okay, let's think about the neural network for the double match point, because that's the easiest to understand. On a backgammon board, there are 24 points and the bar, right? And for each of those 24 points, and for each of the two colors, the player could have anywhere between nothing to 15 pieces, right? And we can encode that with an input neuron, and we set that neuron to equal 1 if and only if there are at least I checkers of color C on point N on the position and 0 otherwise, right? So let's think about it. There's 24 points, 2 colors, 15 different number of cardinality of checkers, 2 times 24 times 15. That's about 700 different input neurons that go into the network, right? These are the inputs to the function. Think of this as a giant math function that takes your board and tries to compute the probability of you winning. Similarly for the bar, for the two players, how many checkers do they have on the bar? It could be anywhere from 0 to 15. And double match points are symmetric, right? You can evaluate every position from the point of view of the player on move, right? There's no preferred side, right? Nobody's winning in a double match point. And our output ranges from -1 to +1. -1 means that we're guaranteed to lose. +1 if we're guaranteed to win. In between that is basically where all the interesting backgammon positions fall, right? What about for our cubeless match point? You're going to encode your board similarly, right? However many checkers are on each point, how many on the bar. But now you got to encode whose turn it is, right? Because we're not symmetric anymore, right? Is it the match point player that's on move, or is it the opponent, right? And you have 4 different outcomes, right? And so we need 3 different outputs. One of them indicating the opponent has won, one indicating that he has won a gammon, and then a backgammon, and everything else, right? 1 minus the probability of that is the probability of the match point player winning. Now here's the interesting case, and here's where most of the interesting work happens. You have cubed rounds where the players could potentially double from here on in. We got to encode the board, and we got to encode who has doubling privileges at this moment, right? They could both have doubling privileges at the same time if the cube is centered at the beginning of the game. And what's our output? Well, either player could win, right? And either player could win 1, 2, 3, and this one's 4 or more points. And very rarely does a game get doubled twice and then have a gammon, or doubled 3 times. And so we're going to kind of approximate by assuming that for the most part the game is only going to go on to 4 points from the current situation, right? So for example, if we evaluate a position where the doubling cube is already 2, this is really the probability of winning 2, 4, 6, 8 points starting from this position, right? And very rarely do games go on to double multiple times and or have a gammon at the end of doubling a few times, right? Which is why the doubling cube was invented in the first place, right? To get rid of a lot of those lopsided games, right? Now as a control, we also learned the money game. We got the points, the bars, and the doubling privileges, and in this case, we're trying to estimate the expected score, right? Plus or minus, depending on if we win or lose. Now, what do we do to learn the network? Basically, reinforcement learning. The idea is to learn by playing through billions, actually more like trillions of rounds, and making optimal moves and doubling decisions based on the current network configuration. And then as we make that move, we might realize the score is completely off, and then we got to learn the new score and fix those errors with backpropagation in the neural network, right? So once we have our network, how do we make use of it? Well, remember, we were given the probability of winning 2 points, 3 points, 4 points. We got to put some value to, well, what happens if I win 4 points? And that's where the match equity table comes into play. This is not my work. The match equity table is basically the probability of winning a match given the current score. It's been studied extensively, and we have a table up to 15. So how do we make use of that now? Well, our evaluation function, as you recall, gave us the probability of winning various number of points. And so suppose we're 5 away, 3 away, we got a probability of 0.4 of winning exactly 1 point. And if we win 1 point, we go to a position that's 4 away, 3 away. We look up on the table what it's worth, and basically we're computing an expected value, right? So let's take a look at some results. We tried our program on the opening rule, and it claims that the best opening rules are the 3-1, the 4-2, the 6-5, the 5-3. The worst are the 4-1 and the 2-1. Pretty common sense. And then we tried matching up our network versus just using the doubling window for the money games. And very statistically significant results, 63-12 to 36-88, playing a 5-point match. Now, some open problems that I'm kind of disappointed to not have time to get to. What about the endgame tables if we have cubed games? Or part of the problem with the endgame table is that if you use the doubling cube, remember, scoring 4 points is not exactly double the value of scoring 2 points, because you got to worry about the match equity table, which means that your endgame table base is going to blow up, right? Because each of these cells is going to become its own table. The table as it is already takes up about 10 gigabytes, right? So that's not feasible with the hardware I have today. Maybe we can approximate it and trade off some accuracy for space, right? Now, most backgammon experts know that when you're 2 away versus n away, the strategy changes considerably, right? Our networks only take into account 1 away. And obviously, in order to calculate the network for the 2 away game, you kind of have to know a little bit about the 1 away game in the first place, right? Because 1 double when you're there, right? So you're kind of reinforcement learning off of the 1 away. So we want to master that first, make sure we have everything right before going on to the 2 away problems. One thing I didn't do because of time constraints is making use of the neural networks to kind of verify the match equity table and perhaps even improve it, right? If we know a good strategy, we could potentially play out lots of games starting from a certain score away and seeing if they line up with the match equity table from previous work, right? And I'm kind of inspired, given the results I got for this project. I've kind of been inspired about how to use neural networks for contact tracing during the pandemic, right? You imagine you have people going about their business, you got data points about what they've been doing, and then a couple weeks later some people get sick, and can we model that as some kind of a mathematical function like that? Who got sick? What did they do? Bang, 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 bang. We have 8 months of data right now for COVID-19, and we had other pandemics before COVID-19 as well, right? I hope to do that at some point. Thanks for watching.